Engineering can design the perfect material for a part, but economics decides what actually gets built. Materials that look great on paper may fail the budget or schedule test. Raw material price, tooling investment, supplier capability, lead times, and certification overhead all shape decisions. Program managers balance performance goals with procurement risk and cash flow. The final structure is as much an economic product as an engineering one. Manufacturing methods: stamping, machining, automated fiber placement, AFP, resin infusion, forging, or additive manufacturing change what's practical and affordable. A material may be structurally ideal, but impossible to make at scale without huge capital tooling. For composites, AFP and automated tape laying enabled large carbon parts, but required big equipment investments and process development. For metals, high-speed stamping and CNC machining favor aluminum and steel in many parts. Match the part design to the process early to avoid costly rework. Every material decision is a cost or performance compromise. Composites give weight and fuel burn benefits, but carry higher material costs, longer cycle times, and higher capital expenditure. Aluminum is cheap, fast to make, and easy to repair, but heavier. Titanium buys strength and heat resistance where needed, but at notable premium cost and processing difficulty. Meaningful comparisons must include fuel saving, maintenance, scrap, and end-of-life costs, not just the sticker price per kilogram. Lifecycle cost goes beyond acquisition. Repairability, inspection time, and depot capabilities drive operating expense. Composite repairs often require controlled curing and trained technicians, plus specialized NDT, ultrasound, thermography, whereas metallic repairs may be quicker and cheaper in many line maintenance contexts. Hidden damage in composites can increase downtime and inspection cost. A higher upfront material cost can be offset or magnified by maintenance realities. Studies and operator data must feed material choices early in a program. Production rate is a hard constraint. High-volume airliners demand processes that can be repeated reliably at scale. Automated processes, AFP, automated tape laying, increase repeatability but require huge capital investment and ramp-up time. And they create a new bottleneck if supplier capacity lags. If you need thousands of parts per year, manual composite layup may be impractical. Conversely, low-rate specialty programs can absorb higher per-part costs. Plan manufacturing capacity at the program level, not the part level. Airlines care about seat mile cost, dispatch reliability, and maintenance predictability. A lighter airframe reduces fuel burn and CO2 emissions, big win. But airlines also weigh acquisition financing, residual value, and maintenance network compatibility. Operators with large, hub-based fleets might prefer materials that reduce fuel burn even at higher purchase price, while low-cost, high-cycle regional operators might favor rugged, easy-to-repair metals. That real-world operator perspective often drives OEM choices.